a very respected and honorable speaker, Professor C.K. Chanda with us. When Professor Datta actually posted this one, that this will be our next webinar, the topic actually caught my interest actually. I know photon, I know electricity, I know sun, I know human, I know interconnection, but I do not know that photon to electricity and sun and interconnection together. So it is a very interesting topic, I think, and we are really thankful that Professor Chanda has given his consent, who is a very renowned professor of Electrical Engineering Department of IIEST Shibpur, previously it was B College. So I thank Professor Sukha for his Electrical Engineering Department, and then senior Professor Sumit Banerjee is also there, Dr. Chanda is also there. Many of the other faculties are there, and almost 100 participating students are also there. So I believe that it will be one of the most interesting sessions. Before I conclude, I just want to say, because so many students are also there, that dear students, you will be very happy to know that our college has held a national footprint. On 14th actually, we got IICT Idea Lab project. It's a very prestigious project all over the country. 204 participants were there. There are many big colleges, and out of which 152 were screened out, and 49 they selected. So out of this one, only 2 colleges from West Bengal got this selection. One is your that is HIT. One is HIT, and another one is our college. So only 2 colleges got selected. So it's the right moment for all of us. So before I conclude that, I once again thank Professor K. Chanda for giving his very valuable time, and with a very outstanding, I should say, a very interesting topic, electricity, sun, human interaction. Thank you, Professor. Thank you. And when this pandemic will be over, I would invite you to come over our college physically and interact with our students. Thank you, and this session will be very interesting. Thank you.
Okay, thank you, Director, sir. Thank you.
Now I request Professor Sumit Banerjee, sir, to introduce us with CKC, sir, with his brief profile, and please ask him to enlighten us with his speech. I would like to ask the audience that if you have any question about the upcoming presentation, please type it into the chat box. I will try to bring it to the notice of sir. Thank you. Sir, okay, over to you.
Thank you so much, Senasis. Okay, about Dr. Chandan Kumar Chanda, Dr. C.K. Chanda is working as a professor in the Department of Electrical Engineering, IIEST Shibpur, India. He has earned PhD degree from the Department of Electrical Engineering, basically B College Deemed University Shibpur, with specialization in power system. Dr. Chanda has over 31 years of teaching and research experience in the diverse field of power system engineering and almost 5 years experience in industry. His area of interest include smart grid, resiliency, stability, and renewable energy. He is a recipient of Tata Rao Gold Medal. He has published 150 research articles in reputed national, international journals and conferences, including 50 research papers in SCI Scopus Index journals. He is a member of the editorial board and guest editor of numerous reputed journals. He has authored and co-authored 7 books in reputed publishing houses like CRC Press, McGraw-Hill, PHI, and Springer. He has contributed 7 book chapters in international proceedings. 11 research scholars have got their PhD degree under the supervision of Dr. Chanda. Currently, 8 PhD students are pursuing under him. He has visited different foreign countries, including USA, UK, Australia, Japan, and China for academic purposes. He is the senior member of IEEE USA, member of IET UK, fellow of Institute of Engineers India, chartered engineer, and live member of IST. Apart from all of his glorious professional achievements, he is a nice, kind-hearted, and down-to-earth personality. I am blessed that I have been attached with him for 32 years, that is from my college days. Thank you, sir. Sir, please deliver your valuable and informative speech, sir. Thank you, sir.
Okay, thank you so much to all of you, and good evening to all of you. Good evening to Director Sir, other eminent professor of your institutions, and all the my dear beloved and lovable students. Because I believe the target audience is my students, and in some point of this speaking directors are also very interested to listen the sun human interactions, I mean from photon to electricity. Anyway, so let me present my article, what I wanted to present now, your entire screen. So I'm trying to present the thing now in front of you, what I wanted to tell you. Yeah.
Yes. Okay. Okay, thank you. I am sharing the link over the WhatsApp and to other students. Thank you. Sorry for the interruption, sir.
Yeah, no issue, no issue. These are the thing comes in detail, no
Thank
issue.
you, sir. I am sharing it.
Now my question is whether it is visible to you, this presentation.
Yes, sir. Yes.
Yes, sir. Yes, sir. It is.
So this is my habit, because we are all far away from, say, maybe 180, 200 kilometers away. So it's my very, you can say it's a bad habit. Sometimes I want to take feedback from you, whether I am audible or not, whether, because all you are dependent on internet and electricity. So let me start with this photon to electricity. It's a very interesting topic, in fact. Let me start with a little bit introduction of why we are talking about photon to electricity 2021. And we are talking about sun and human interactions, because sun was there, at least as per the data, as per the statistics, the sun is existing for 4.5 into 10 to the 9 years. So the sun is here. Even if we do not talk about this in 4.5 into 10 to the 9 years, if you go back for 500 years or 700 years, we used the sun in a number of ways, for drying foods, for drying clothes. There are a number of applications for burning paper through the lenses. So these are all not the new issues. These are all old issues, and we applied in a number of ways. And in fact, for that reason, in different countries, including India, we worship sun as a god. But now, of course, sun is a god. But now we want to treat the sun as a power station. And this power station is not made by human being. This power station is gifted by God, located in the sky, and from that power station, we have to extract the power. The power station generally, students, is man-made. Either it is a hydrothermal, or it is a kind of a solid fossil fuel-based power station. This is there in the Durgapur area, Divishi. Not that kind of power station. This is a power station gifted by God, available, located in sun, and you want to extract power from that. And that amount of energy, infinite amount of energy you can extract from that sun. But how? That is our question. So let me start with the word energy. In fact, we find in every symposium or seminar or webinar, the way we defined or conference, it is related in some way or other the energy. So the way I am conducting this deliberation, because of the energy, electricity is available, and this internet again requires kind of energy. So it is all about energy right from the morning to night. Without energy, we cannot do anything. We cannot imagine a single moment without energy. But the question is, in the back of our mind, this energy mostly 99% we are extracting from the fossil fuels. Fossil fuels means, may not be it is a solid one, it may be liquid, either in the form of a solid, I mean the coal, or the nuclear fuel, radioactive stuffs, I mean the uranium, or in the form of a liquid, petrol or diesel, or in the form of a natural gas. In every state, this is available. But the question is, those are all finite. And let me give a very small statistics behind this. We are thinking, we are thinking in this direction, we have to extract energy from sun. The reason is all these energy resources or the energy carriers. Coal is an energy carrier, petroleum is a good kind of energy carrier, and that's why we call all these things a primary energy carrier. And then this primary energy carrier, with the help of engineering and technology and science, we can convert to usable energy, electricity. And mostly 99% we receive from that energy. Even this deliberation I'm conducting from CSC Power, Calcutta Electric Supplies Corporation Power, and that is mostly 95% comes by burning coal only. But the question is, where from this coal has come? This coal has come from biomass. But how many years have taken from converting that biomass to coal? Million and million years. But let me tell you, 1882, the first transmission line we developed from New Jersey to New York, 1882, and 2021, count maybe 139, 149 years, or better for simplicity sake, 150 years. In 150 years, whatever coal is accumulated by the natural process by 1,000 and 1,000 years, by million and million years, we are now calculating the amount of coal, how much coal will be existing for the next future generation, maybe 40 to 50 years. So within this 150 year span, we are going to exhaust everything. The reason is simple, because it is finite. It can be depleted. As far as the coal is concerned, as far as the natural gas is concerned, as far as the petroleum is concerned, even as far as the radioactive stuff is concerned, uranium, everything is to be depleted very soon, within 40 or 50 years, as per the statistics or as per the data available. So the next alternative to our engineers' mind, to the technological people's mind, what are the alternative sources? It is not that we are going to last for another 40, 50 years. This world, this earth will move on for next 1,000 years. So next 10,000 years. So what is the alternative sources? So that we have to think. Because these things, after 50 years, will come to a point where 1 ton of coal will be available in this planet. Only 1 liter of petrol will be available in this planet. So after that, 1 liter of petrol, 1 liter of diesel, and 1 ton of coal, what we will do? We will stop all the processes? The answer is no. Science, technology, scientists, technologists, and engineers are running after, and they are thinking a lot how to go for the survival. And of course, if there is a problem, we know there is a solution. Like a proverb, if there is a smoke, definitely there is a fire. So similarly, if there is a problem, if we feel it, these are the finite sources, it will be depleted very soon. So there is a solution, and this solution is the alternative forms of energy. Out of all these alternative forms of energy, the first thing comes in our mind is the solar energy. There are other forms of energy, of course, the wind energy, hydrothermal energy, and the geothermal energy, tidal energy, wave energy, fuel shell. There are varieties of the things out there, but solar energy is one of the important form of renewable energy. Now, let me clear you one thing regarding this thing, because the major target audience is why it is renewable. Renewable means this energy is infinite. It is not like coal, it is not like petrol, it is not like a radioactive element like uranium. We can generate it again and again. The one aspect is renewable energy. And let me clear you one point here. Sometimes we utter this word, renewable energy is very clean and green. In every seminar I have found it, I have heard it. So what do you mean by the clean and green energy? If you call it the sun energy is another form of alternative. Clean is okay, because the solar energy or the energy what we are extracting from the sun, it does not emit carbon dioxide, it does not emit carbon monoxide, it does not emit mercury, it does not emit methane gas, it does not emit SOx also. So it's clean, no issue. It does not give an impact to the environment. Because whenever we will talk about the energy, climate change, in fact, now G7 is going on in Cornwall in UK. In fact, 5 years back, I was in Cornwall. So in UK that is going, because that is the climate change issue, and all the important personalities like our Prime Minister, all they are thinking, because the climate change, and even not as an engineer, even an ordinary man, even my mother can visualize. Her age is 87 years old, 87. She can also visualize what is climate change. In every year, the May of month is booked for super cyclonic storm. We have never heard 25 years back super cyclonic storm coming in a different names. Umfan, Yas, then that something come in Gujarat area in the western part of India. So a lot of the cyclonic storm, and in US in every month they are facing this kind of super cyclonic storm. Why? The reason is the climate is already got damaged. We have already wounded our Mother Earth. Now we don't want to hurt our mother. This is one aspect, climate change. Other way around, another aspect is the population across globe, across world is changing exponentially. I mean, in the rising side. So this is one aspect. And another aspect is this, why the demand of energy has gone up to that extent, changing exponentially. Another aspect, because another important point, not only the population change and all that going aspect, another aspect is the rising standards of living. Almost in every house nowadays, the micro oven, then the double storage fridge, 3 or 4 laptops, multiple mobiles, then 3 or 4 ACs in every room, huge amount of rising standards of living. So energy demand is continuously changing in the upward side. So you have to find an alternative. So these are the issues. In fact, during 1970, crisis for oil compelled to look for different types of resources. And I am particularly in my deliberation concentrate only on the solar energy. Because solar energy, so as far as the clean water is concerned, I am sure it is clear to you because it is not emitting pollutants. Now what about green? And because it is not an offline interaction, why this solar energy can be called as a green energy? It is not exactly green energy. It is green energy dependent on the location. If you put the solar panel where flora and fauna is not affected, environment is not affected, forestation is not affected, there the solar energy is a clean and green energy. But because of this, if the forestation is affected, if the flora and fauna is affected, it is not a green energy. So if we claim solar energy is a green energy, we have to specify the location. If we put all the solar panels in the Sahara Desert, so solar energy can be considered as a clean and green energy. But if we put the solar panels where some amount of greenery is sacrificed, it cannot be called as a green energy. The way we call the wind energy is not a green energy, because in case of a windmill system or wind energy derivation, a lot of birds get died because of these long blades and all that. So green is that where we're not going to damage our environment. So solar energy, absolutely clean, no doubt behind it. As far as the green, there is a big question mark, depends on the location. But here at this point of time, at the end of this deliberation, sometimes students ask, sir, if you put all the solar panels in the Sahara Desert, how does it matter? It's good. Then the question is the temperature variation in the solar desert is tremendous from the daytime to nighttime. How the semiconductor physics will work, that is very important issue. And if we generate the total power of this earth at a particular point, imagine what should be the distribution and transmission line. That we cannot. It should be in the distributed form. The total power of this planet is generating at a particular point, then we have to bring this power. Till today, we give power, electrical power through conductor, through physical conductor. It's not that the internet, it's not that the telecommunication without wire it will go without wire. We need conductor, we need physical conductor to give power to the loaded, to the consumers. So if all the power is generated in the Sahara Desert, how it will be distributed across this globe in the different countries? It's another issue. So we have to take it. Granted that we have to distribute the solar panels in the different parts of this. And another important point, let me tell you, sometimes Again, students ask, I am putting my question from students' behalf and answering it. Sir, sun is available during the sun. What about the night? God has again taken care of this. That's the plus point of God. Generally, wind flows generally in the night and in the morning time. So in the morning time, light intensity is less, but wind is there. Even in the night time, so it is complementary with each other. If you can able to use the energy in a very optimal way, this natural energy, so we'll able to extract the power from the wind in the night time and from the day, from the sun. This is okay. So sun energy and wind energy is complementary with each other, and that God has given both. In night time, sun is not there. It does not mean that during the daytime wind is not there, but the flow of wind is inner. There is a some solar phenomena is there, and that I'm not going to explain. There is a different aspect, of physics, and because of that, the blow and flow of the wind during the night is more compared to the daytime. And what I wanted to tell from that, because of all these things, because of the increasing of the surface temperature of the sea and all that, every year you're facing cyclonic storm, get a change and all that. So we have to go for the energy, that kind of energy where at least it should be clean, if not green. So these are the things are there. I mean, from photon to electricity, I'll choose only silicon. Again, let me tell you why I have chosen silicon. And most of the solar energy generation is silicon based. Why? Because silicon dioxide is available abundantly. If you go to Sahara Desert, I don't think there will be there will be deficit of silicon dioxide. If you go to any seashore, you will find silicon dioxide. So silicon dioxide is abundantly available. Sun is absolutely free to us. Till today, nobody has taxed sun. Nobody can put GST, CGST or SGST on sun. Sun will never claim, though I have given this much amount of radiant power to pay money tomorrow. So nobody is going, there is no kind of that kind of business or philosophy is there between the sun and this energy. This is one aspect. And another aspect is that it is absolutely clean. So all these issues you have to club together, we have to aggregate together, and we have to utilize it. And here the question comes, sun. So almost 10 billion people of this world desire stable climate, stable health, and stable economy. Stable climate, I am not going to explain. Every year we are facing cyclonic storm. 10 lakhs people of our state is now in the devastating state. Stable health, I am not going to explain due to this environmental problem. Last 1.5 years, everything is almost collapsed because of the COVID-19 situation. So we do not have the stable health condition. Again, because of this. If you go to diff into the corona, you'll find again that is responsible. That the climatic condition is responsible in some way or other. And because of this stable climate, unstable health and all that, you see everywhere the economy is not stable. Absolutely free, poor scenario of the economic conditions. I'm not talking about our country, across globe. So in other way around, this climate change has given a huge amount of impact to the health, huge amount of impact to the economy, huge amount of impact to everywhere. So we have to switch to sun. So these are the things I wanted to mean why we are preferring sun, and human being has to interact with the sun desperately. We have to look at sun very closely, what exactly happening with the sun. Next point that I have already explained, we cannot wait up to the last drop of oil, last ton of coal or last kilogram of oil. You cannot wait. We have to go for a paradigm shift in clean energy production, because the time is very, very tight. And we want desperately to stop the climate change. Otherwise, everything will be unstable. From economic point of view, from health point of view, everything. And if we calculate 1,74,000 trillion, possibly, what is trillion? That trillion is nothing but 10 to the power 12. And that scale we are talking about, 10 to the power 12 is tera. So 1,74 trillion watts are falling from the sky at any moment of the earth. And every moment we are receiving this amount of, this is on the surface of the earth getting. Payback time is also gradually reducing day by day because of the advanced research in the field. ICT has come, information technology, computer technology, artificial intelligence, machine learning, robotics, blockchain, lot of advanced technology has come. So there is no dearth of technology. So payback time is gradually reducing day by day. And sun is available almost 10 to 12 hours in a day. So we have to club together this idea. Just a mere calculation I have given. On an average, we are getting 1367 watts we are getting on an average on Earth's surface. And roughly speaking, this is the irradiance. Solar irradiance, there is one term, there is known as insulation. Those who are from the solar energy field, they know that is known as insulation or solar irradiance. But roughly speaking, if we take the average for the total day for 12 hours from dawn to dusk, then it comes in the order of 1000 watt per meter square. And here, let me tell you one point: 1000 watt per meter square, the solar energy is known as one sun. Whenever you talk about solar energy, there is a unit. This is known as one sun. One SUN, sun. One sun means 1000 watt per meter square at sea level. That is the point, and at 25 degrees centigrade. So we calculate, we can able to calculate the area of the surface, able to calculate the surface area of this planet Earth. No issue. That the radius of the Earth is known to us. So if we go with this, we can calculate 175 million gigawatt power we can generate from the surface. It is almost equivalent to 84 million Hoover dams. Or in other way around, whatever the energy we are getting from the sun, we can able to utilize that energy for 1 hour. We can able to manage for the whole year's consumptions of this planet. So whatever the amount of energy is coming from the sun, if you can able to utilize for 1 hour only, the whole planet's energy consumption is covered. I'm talking about the advanced country, but the per capita electrical consumption is more. I like USA, Japan, and Canada. I'm not talking about Bangladesh and India. Our per capita consumption is very, very less compared to other advanced countries. It covers the total globe. If you're able to utilize 1 hour of solar energy, imagine. And how much time the sun is going to last? The sun is already there for 4.5 into 10 to the 9 years. It is again going to last for 5 into 10 to the 9 years. And if we, what does it mean? Sure, what will happen after 5 into 10 to the 9 years? We should not think about it. Because in a human time scale, this 5 into 10 to the 9 years is an infinite span. We should not think about it. What will happen after 5 into 10 to the 9 years? Let us think for another 1000 years. Let us think for another 500 years how we are moving the energy paradigm, energy side. So that is very, very important. And why? The question is why? Because inside the sun, so this is the thing, the sun, I'm not going into details and all that. So let me come to the sun. Beside sun, you see, this is the core part, the bright part. Can you see this diagram? Sometimes I will take a feedback from you. Can you see this core part?
Yes, sir.
Okay. If you say yes, then I will be happy because one can able to see our face because of this internet kind of virtual mode of teaching or deliberation. This is the core part. In core part, mostly hydrogen is here and helium is there. So this hydrogen is converting to helium. The first step. In fact, in 3 steps it is converting. So this interaction I want to do. And whenever this hydrogen, one of the lightest material is converting, in fact it is a gas converting to helium, the another lightest thing, it is radiating huge amount of energy. And this energy you want to extract. So this energy we cannot extract. In fact, if we can extract this energy, then whatever the amount energy will get in 1 second, it is more than enough to cover this whole planet for the whole year. So that we are not going to extract, and no one can extract. So this is the thing is happening, and from I told you, another 5 into 10 to the power 9 years will exist the sun. It means the amount of hydrogen is there inside the sun in such a way it will be exhausted. This reaction will be stopped from hydrogen to helium conversion will be stopped after 5 into 10 to the power 9 years. That time there will be no radiant energy, will not get energy. But imagine, I am telling you again, 5 into 10 to the power 9 years. But we are thinking for another 1,000 years, for another 2,000 years. And if we think for another 2,000 years, which compared to 5 into 10 to the 9, is nothing, in fact. So from this is the core part. After this core, this is the radioactive zone. Radioactive zone, after that, this is the convective zone. After convective zone, this is the chromosphere. After chromosphere, there is a zone that is known as the corona. And in fact, in solar eclipse, by your open eye, it is harmful for your eyes, of course, but your open eye, whatever you can find, that is the corona part. I am not talking about this COVID-19 corona. So this corona we can see in our through our direct eye during the full solar eclipse, this corona. And at corona, the temperature of the sun is in the tune of, it is written somewhere in my data, it is in the tune of 5772, something like that is the temperature. But at the core, temperature is the tune of 1.5 into 10 to the power 7 Kelvin. But at the corona part, I mean in the photosphere part, this is the photosphere part, and this is the chromosphere. Chromosphere we can see through our open eye, but photosphere we cannot. In this photosphere, the photon will come, which will convert the electrical energy. The photosphere, the temperature is 5772 Kelvin. So whatever the photons we are receiving from the photosphere at the temperature level 5772, we are going to utilize it. Not from the core part where the temperature is 1.5 into 10 to the 7 Kelvin. This is things. And sometimes the students ask, sir, if I consider 100 watt bulb we are creating in every second, if I create 100 watt bulb, so how many bulbs will be required or how many years will be required to create a sun artificially? Of course, we can create this artificial sun, but it will take, because from the sun we are getting 3.83 into 10 to the power 26. Remember the indices, remember the power. 3.83 into 10 to the power 26 watt power we are getting from the sun. And we know from the basic definition of watt, 1 joule per second is 1 watt. So we convert this joule to a watt. So 3.83 10 to the power 26 watt amount of energy you are receiving from the core part of the sun. So if we go diverging out slightly from our discussion, so if we want to make artificial sun in this planet, it will take generally 4.5 into 10, compared to this, if we want to convert this, it will take 10 to the power 17 years to create a sun. In every second, if we can form 100 watt incandescent lamp, because why I have chosen incandescent lamp? Because incandescent lamp give a polychromatic light, the white light that we know. It's not like sodium vapor lamp. You have not doped certain amount of sodium vapor, the color of the light is different. Similarly, whatever you are getting from the sun, we get Vibgyor. All kinds of lights are there. And from our class 10 standard physics, if we club together all the light, it's nothing but the white. So it is a polychromatic light we get from the incandescent lamp, and will take 10 to the power 17 years. It will take time to create an artificial sun. If we go on producing 100 watt bulb in every second, imagine it is not feasible by the human being. 10 to the power 17 years time will be take, and normal human beings workable phase is in the tune of 30 years. So again with that time span, in that time scale, it is nothing. So we are not going to create the artificial sun. Whatever maybe the blockchains, artificial intelligence and technology comes, we cannot create in any way. Again, we have to believe in that sun, the power and all that. So what is happening with that sun? For that, we have to understand a little bit quantum mechanics. What is quantum mechanics? Because until and unless we understand quantum mechanics, we won't be able to understand these things. Because whatever you're thinking in a mega level, 10 to the power 6 level, not in the rather the mega level, rather giga level and and tera level, trillion watts level we are thinking. And for that reason, we have to go again in the opposite side, in the reverse mode, in the nano scale, in the micro scale, in the pico scale, we have to think. Let me explain what is now quantum mechanics in a very simple language, because I always prefer to give an example whenever I go for deliberation. It is my bad habit I always try to explain everything with the form of an example. Whenever we write something with the help of a chalk on a blackboard, the chalk is having a length, good length. We can hold that chalk and can write. And whenever we put some impression on that whiteboard or blackboard, whatever it may be, we are using Newton's second law, P is equal to mf. We are giving certain amount of force, and because of that force, some impression is coming on that blackboard. So this is Newtonian physics. But if we go deep into the sun, this Newtonian physics not work. And nobody can reach to the sun also, because the temperature level in Kelvin, at least in this photosphere level, is 572. So you have to go with the microscopic, not microscopic, rather the nanoscopic level. So whenever we'll think everything in the nanoscopic level, we have to go for a nanotechnology. At the same time, you have to go for a quantum mechanics. So let us think that we'll go on breaking the chalk. The chalk has a dimension, you can hold the chalk, and where you can apply second law of physics, Newton's law, P is equal to mf. We keep on breaking the chalks. If we go on breaking the chalks in such a way, the dimension has become 10 to the power minus 9. We have brought into nano level, nano scale, we have brought that chalk. The point is that we cannot hold that chalk in the nanoscopic level or in the microscopic level. We cannot hold it. CKC cannot hold that microscopic level chalk size. Even though the feature characteristics of the chalk will remain the same, and we cannot write it, and we cannot apply the force. So we have to understand a quantum mechanics a little bit for conversions from this. And whatever the energy is coming here, that is again coming in the form of a quantum tunnel. This radioactive energy, just like that, is not coming. It is coming through the quantum tunnel. So what is coming within this quantum tunnel? In the quantum tunnel, it has come the electromagnetic spectrum. And in this electromagnetic spectrum, within this electromagnetic spectrum, if I'm not wrong, more than 15 scientists got the Nobel Prizes, including Albert Einstein. Albert Einstein gave the concept of photon, light energy, in 1905. After 16 years, I mean 1921, I mean now 2021 is going on, 2021 is going on, just 100 years back. After 16 years, the theory is accepted and got the Nobel Prize for this photon, not for relativity and all that. Sometimes the student get confused. No, he has got the first Nobel Prize from photon in 1921, even though he gave the concept in 1905. Then Rutherford came, Niels Bohr, Planck, series of scientists came in the electromagnetic. Rutherford, they came into that zone and got the Nobel Prize and the change. And we are utilizing those proofs in the technological aspect. Now, at least we want to. We do not want to wait for the last ton of coal. So, with the ideas of their great scientists, those who have got the Nobel Prize in the electromagnetic domain, we are utilizing that quantum mechanics, very interesting mechanics. In fact, I love that subject. And from there, this energy getting converted. So this is all about sound. So know your sound, the blackboard and all that, I'm not going to have already discussed. So now let us come to the radiate energy, because our target, whatever the energy we are getting from the sun in the form of quantum tunnel, we have to convert to critical energy. What is coming in the form of radiated energy? It is electromagnetic spectrum. Again, the electromagnetic spectrum, if we analyze, we'll find gamma rays, X. In fact, before gamma rays, another ray is there because of this. And the length of the laptop, I could not able to accommodate another ray, there cosmic rays, but these are not important from solar energy perspective. So I have not taken intentionally gamma rays, X-ray, ultraviolet rays, visible rays, infrared, microwave rays, and radio waves. So these are the things are there inside the electromagnetic waves. Electromagnetic, they are having dual properties, electrical properties as well as the magnetic properties. But out of all these waves, we only can use the visible zone. Visible zone means the pure zone we utilize for converting lead. So sometimes the students ask at the fag end of this lecture or sometimes they share this 1950 the PN junction diode started. 1954 Bell had developed the photovoltaic cell. 1970 there is a crisis of oil. We have started developing the photovoltaic cell for solar generation. In 2021 we are talking about the solar cell with efficiency is only 15 to 20%. Why share? So last 70 years, we could not able to improve the efficiency of the solar cell from 10% to 30%. Of course, in academic interest, in theoretical level, in mathematical way, in numerical way, we have gone up to 35% efficiency. But in a real sense, in a reality, the efficiency of the monocrystalline solar structure what is available in the market, most of the generation we get from the solar energy from the monocrystalline structure in the tune of 15, 16, maximum 20%. Student, why share? So much involvement in the computer science, the technology, the smart grid, renewable energy and all that, why not? Even the memory side, whenever, I mean, if I can remember correctly, when I was a student, used to use the floppy disk. In the floppy disk, we used to store the information in the form of kilobyte only, 1 kilobyte floppy disk. But very recently, I purchased one memory device of 5 terabyte. So 1 kilobyte to 5 terabyte, imagine, within a span of 30 years. So such a change in the technology. But what about the solar cell? Solar cell started with a 10%. After 70 years, only 16%, only 6%. The simple reason, if you look at this electromagnetic spectrum, whatever the radiant energy coming from the sun, only the visible part we can utilize it. The other parts are completely useless. The question again, why? Why is that the visible part is only we can utilize for the solar energy for conversion from photon to this part? Why not the other part, the gamma rays, the cosmic rays, the X-ray, ultraviolet, microwave and radio? Even the full part of the visible we cannot utilize. So imagine whatever we are getting in the form of radiate energy, we can only utilize only from this frequency level to this frequency level. I have taken an example also. Because whenever I will restrict to the visible part, I have to think for the VIB. See, only because this radio wave, microwave, X-ray, gamma ray, cosmic ray, we are not thinking. We are thinking only the vision part, which is caused by the parenthesis brackets. And we know as a student, as you are all studying engineering, know from the physics why the sky looks blue. Because the relation with the energy and frequency and wavelength. Because in case of a red light, the wavelength is more and frequency is less because frequency and wavelength are inversely related. In case of a VIB, because blue and green kind of thing, their frequency is more and as frequency is more, it immediately reflects back to the Earth's surface again, and that's why the sky looks blue. That is the only reason. This is 10 standard or 11 standard physics question, why the sky looks blue? Because of the reflected ray. So from there he got an idea, again for conversion solar energy, whatever the radiant energy we are getting, that energy cannot convert to these things. Certain amount of energy getting diffused, certain amount of energy getting absorbed, certain amount of energy getting reflected back to the atmosphere again. And that is again a greenhouse effect for the positive. So sometimes we say in the conventional delivery, greenhouse effect and all that is very bad for the climate change. No, not at all. If you go into deep, greenhouse effect is, if there is no greenhouse effect in the atmosphere, the temperature of this planet could have been minus 20 degrees centigrade where no life can live. So greenhouse effect is required. But nowadays, the way we are burning the fossil fuel, the reverse effect of greenhouse effect has come, and that's why the climate has changed like anything. And super cyclonic storms, corona, then the variants of corona plus, different variants are coming, and first wave, second wave, third wave, fourth wave, fifth wave is coming, and the whole thing has got damaged. Because greenhouse effect is required to make the temperature to AC and all that. So imagination how much the toxic acids we are throwing to this atmosphere. Which are all, I mean, the cumulative effects to the atmosphere. And we have damaged the greenhouse effect. So let me come to the physics part. So Vibgeo. And we know the wavelength and energy, possibly you can see from this diagram, when wavelength is moving to this side, energy is moving to this side, means they're inversely related. And from this famous Albert-Einstein's equation, E is equal to H into nu. H is the Planck's constant. And possibly you know, H is this Planck's constant. Planck has defined the atomic energy level. He is the man who given the definition of energy in the atomic level. In the atomic level. Atomic level means in at least 10 to the power minus 18, the size is the double smaller of the nano size. So ultra nanoscopic level. He has defined the atomic energy, and that gentleman has developed a constant, which is Planck's constant. So red light, 700 nanometer is the wavelength that I have not assumed. I have collected from the data. It is available in electromagnetic spectrum. This is the famous equation. The speed of light in the vacuum is nothing but lambda into frequency, where A is equal to C by lambda. So I want to calculate the frequency. Before that, let me slightly, let me come back to this slide in a. I am doing the mistake. Yeah, sorry. Yeah, the next slide is this. Energy is equal to H into F. Energy is nothing but Planck's constant into F. F is the frequency. In general, standard expression is equal to H into nu. But to make you understand very clearly, instead of nu, I have considered H. What is this H? Planck's constant. What is nu? Nu is nothing but the frequency of the photon particle, because you are calculating the energy of the photon. And where photon lies? Photon lies on the vision part only, that I have already explained. So I am calculating 6.6 into 10 to the minus 34 joules again. This is Planck's constant. And the frequency I have calculated 4.26 into 10 to the 14. So that way the energy we are getting 2.84 into 10 to the minus 19. This is the energy we are getting from photon. From which photon? From one photon. From one photon we are getting 2.84 into 10 to the minus 19. So this energy is such a small energy. You see the power minus 19. So minus 19 joule is a very, very small amount of energy. So for simplicity's sake, we are converting to electron volt. 1 electron volt is nothing but 1.602 into 10 to the power minus 19 joule. So that small amount of energy I am converting in terms of electron volt. So 1.773 electron volt. Try to remember this data in the back of your mind. In some point of time, I will require this data. You have to tell me this data 1.773. I have taken this for the red light only in the vision part, and from one photon I am getting 1.773 electron volt. Remember it, this data. So once we can able to calculate the energy of one photon, which is coming as 1.3 approximately electron volt, then we have to use it in the solar shell. It's not that if light falls on my table, wooden table, it will able to generate the electrical energy. It's not that. So you have to pick up such a material which can convert that photon, which is having 1.773 electron volt, to electrical energy. So we have to go to the semiconductor physics. So what kind of material we have to choose for that? The best material you have to pick up from this planet again to make this energy available for all the consumers at the lowest possible price is silicon. Because silicon dioxide is available. Of course, in impure form, we have to give purity to that silicon up to a certain extent. We need not require purest silicon for conduction, for energy conversion. It's not like that diamond, it's not like gold and diamond 99.9999 pure. It's not that. We do not require for electrical generation. 95% purity of silicon is enough, and silicon is abundantly available in this planet. You need not purchase the silicon, only the transportation cost. Of course, germanium is another kind of semiconductor device, very good. Germanium is very good, but germanium is less available compared to silicon, and the ratio is 100. If we get 100 kilogram silicon in Earth's surface, then only 1 kilogram will get germanium. So from the abundancy point of view, from the available point of view, silicon, of course, is a preferable choice for the technologies, for the engineer, silicon. But the funniest part is this, try to understand this physics. At low temperature, if you can remember the atomic number of silicon, it is 14. What is there inside the nucleus? Protons and neutrons are there, the positive charges and all that. And then the cell starts, K, L, M, the cells are there, and cells are orbital, cyclic in nature, but it's not exactly cyclic. To make you understand, the students in every chemistry book, they have drawn some kind of cyclic orbital. It is not that exactly. There is a two-dimensional representation, some electrons are revolving around these needs. And if you distribute the electrons, if you come to the silicon, in the outer cell, 4 electrons are there. And the outer cell is nothing but the valence cell. But the point is that in that valence cell, you cannot knock off any electron at low temperature. So at low temperature, let me tell you one point, silicon is a very good insulator. It's a very good insulator. But again, God has given away, because a human being can live very comfortably at room temperature at 25 degrees centigrade Celsius. That the moment the same silicon, if you bring at 25 degrees centigrade, it behaves as a semiconductor. But originally, silicon is an insulator. Try to remember these things at very low temperature. Again, if you bring this temperature in the tune of 150 degrees centigrade, almost all the electrons of the valence band of the silicon will conduct in nature. The same silicon, even though you know as a semiconductor, it is a very good conductor, like a copper, diamond, like a platinum. So the same metal at different temperatures behaving differently because of this atomic structure. So you have to understand this atomic structure. So you need, and that's why I told you, we have a little knowledge about the quantum physics. Then only you're able to understand how the photon is getting converted to electricity. It's not that I am giving photon, I am giving light, I am putting some light in my water bottle and some electricity is coming out from that. It is not that. What is there? Under intrinsic condition in the semiconductor. What is intrinsic condition? If students know, you have studied normal pain. Achha, let me put you a question, even though you aren't able to answer. Intrinsic semiconductor is a semiconductor. Either it is pure semiconductor, it is not exactly p-type, it is not exactly n-type. Same number of electrons and holes are there. So it is nullified state, it is a neutral state. And during that neutral state, if you want to calculate the energy level of one electron, possibly you know that is called Fermi energy level. Possibly Fermi again got a Nobel Prize for that. Whatever the name I utter here, they got the Nobel Prize. And let me tell you, all the Nobel Prize has come by the equation where 3 letters are related. V is equal to IR, Ohm's law in electrical engineering. That time there is no rule of giving Nobel Prize. We electrical engineer cannot think of electrical engineering. This BE, ME, PhD, everything will be collapsed within a second if we forget Ohm's law, V is equal to IR, at least in a linear circuit. And one Nobel laureate told that V is equal to IR can claim 15 Nobel Prizes at a time. Such a powerful law. The whole branch depends on V is equal to IR. It is not that we are writing a paper, sending some journal, a lot of big equations are there, then somebody, I don't know, your copy. It's not that. Again, come to Albert Einstein's equation. Energy is equal to H into nu. Again, 3 letters connected and got the Nobel Prize. All 3 letters are there in this alphabet, A to Z, but yet connected. E is equal to H into nu. Got the Nobel Prize. No double integration, triple integration, big mathematical derivations and the acceptance of paper. It's not that. We are happy with the acceptance of the paper. They got the Nobel Prize with that 3 letters. Again, energy is equal to mass into light speed square is equal to mc square. How many letters? E, mc. That's all. So these are the things brought the Nobel Prizes. So the atomic physics structure, all the men, the Planck, the Rutherford, Niels Bohr, Fermi, they all got the Nobel Prizes because of these fundamental inventions. And tremendous. Now, this at this juncture of time 2021, 2021, we are again thinking those scientists and trying to convert this energy to the other side. So under normal condition at NTP 25 degree, but pressure does not play a very important role, only temperature 25 degrees centigrade. The average energy level of one electron, like just if I go for the cursor I am showing you, let me choose the laser point, this lies in between. I think you can able to see from your side, in between the valence band and the conduction band. Let me explain what is valence. Valence band is the outer structure. And if from the valence band, the next band is the conduction band where the electrons can move. But remember, let me tell you, conduction band is not the band which is out from the material. It is within the silicon, but after the valence band. Nearest band of the valence band is this. But conduction band, try to remember, it is within the material, within the silicon atom. If I consider silicon as a material and if I think for one atom only one atom, I am explaining for one atom. Now you can go for 1,000 and crores and million atom. But for one atom, the conduction is next to valence band. And the energy level lies just mid of this. But that will not work. So what we have to do? We have to dope the material. Dope means some kind of impurities you have to add it so that the intrinsic silicon will be extrinsic in nature. So what kind of doping? We know the doping, you know, the players, the Olympic players, they go for doping. Doping means some kind of excitation they take outside so that in a small amount of time, they can reach their target. They can reach their destination. So it's the same kind of doping. So this is the doping. So that kind of impurity you have to add. So what kind of impurity we have to add here? So impurity is, if we go for impurities kind of thing, so the point is pentavalent stuff, pentavalent element, which is higher than the silicon. Silicon possibly lies in the fourth column of the periodical table. We go higher with this, say phosphorus, which is pentavalent in nature, and if we add, then one excess electron will be there, because the outer surface of that silicon, try to understand, even though I'm not explaining on whiteboard, 4 electrons are there, and there 5 electrons are in the valence band. So 4 electrons will shake their hand with each other, 1 electron will be extra. So that electron is free nature, it can move, because nobody is there to shake his hand. And if you go with not tetravalent, trivalent metal with that tetravalent silicon, then what will happen is, because 3 electrons are available on the external part of that trivalent material, say boron, so 1 positive hole is created. But I'm not able to show here. Positive hole means it is basically a concept. The students sometimes say how the hole is moving. Yes, hole is not moving. Hole cannot move. The charge cloud is moving from one point to other point. If I able to explain this way, say, forget this one, say this is the Earth's surface. I have digged the surface, a certain amount of soil I have taken out from this. Say I have taken out certain amount of soil from this and I have kept somewhere else. So I have made a hole here. I have made a hole here and lump of soil is here. What I want to mean is an electron. Now, if I bring certain amount of soil from somewhere else, making a hole, and if I pour that soil to this hole, so this hole will not be there. So somewhere the hole will be created. So this hole is not moving. This hole is not moving. Rather, the charge cloud is moving from one place to another place. I could have explained on whiteboard or blackboard, but this is not feasible in a computer. I am not that expert also. So to show everything in the pictorial mode. So that way, show the valence band by trivalent and conduction band. So what will happen? The energy distribution, Fermi energy distributions will be distributed. Whenever it will be N type of extrinsic semiconductor silicon, Fermi level will be closer to the conduction band and below the conduction band. You see, this is the Fermi level I have developed for N type. Whenever we'll go for doping to create a P type of semiconductor, this Fermi level will come to the closer to the valence band and the top of the valence band. So this Fermi level will come to the valence band and will be top of this. So these levels are this. But whenever we'll close together, because this normal P type of silicon will never able to generate this electricity. Normal N type of extrinsic semiconductor cannot generate electricity. We have to add it. We have to join it. We have to go for a junction. It's not that ordinary adhesive, ordinary glue will come, it will join. It's a very complicated process. It's a very, very tough process. How to go for the PN junction. It needs a huge sophisticated environment. And many time permits, you come to our B college, we are having a green energy department. We are creating the PN junction diode. We are producing the solar cell. You can have a look in your own eye. Very complicated process and huge amount of expenditure involved. Our laboratory consists of in the tune of 60 crores rupees. So it's a very complicated process. Not that the way P type of extrinsic semiconductor silicon I will bring and I will bring this and just joined by adhesive. It's not that. It's a heavy, it's a complicated process. But forget it. We are not going into that much detail. We are interested how it will convert electricity. So now our job is to convert this valence band, conduction band of the N level to this. And in that case, in a natural process, this Fermi level will be in the equilibrium state. And I'm trying to showing you, just see. So this is the Fermi level. This is the Fermi level. This is P type of material, you see. This Fermi level is closer to this valence band and top of the valence band. And the conduction band is far away from the Fermi level. So here, number of positive cloud charges are more, what you call as a hole. And here you see, to make it in the equilibrium state, you try to understand this physics. Here, this is the N-type junction where more number of electrons are there, and less number of positive holes are there because the Fermi level is closer to the conduction band and below to the conduction band. Try to understand these things. If you have any doubt, you put me questions later on. So what happens? So to keep this thing in the equilibrium level, that we have to manufacture. In manufacturing Fermi level at a particular point and then P junction, N junction is a very complicated process. But mathematical sake, for explanation sake, we have connected. Now what will happen if we connect like this? Now it is a PN junction. But this PN junction, see, what is the difference between this PN junction and the PN junction you have studied in your 12th standard physics, electronics, or you have studied in your first semester, second semester electronics? You have used the diode PN junction. What is the difference between this PN junction and this PN junction? The difference is that PN junction is basically a sink that consumes power. That PN junction will take power and he will decide the power will flow from one point to other point. So it's unidirectional power flow. But whatever you want to discuss till this time, this PN junction is not a sink. It is not a load. It is a generator. It will generate. So whenever you go for the characteristics, plotting VI characteristics, in case of normal PN junction diode, the VI characteristics comes in the first quadrant. Whenever you plot the VI characteristics of this diode, photovoltaic PN junction diode, it comes in the third quadrant. But I have found a lot of textbooks they have plotted in the first quadrant. This is not their mistake. To make the thing simple, they have done it. But the VI characteristics of the photovoltaic diode will come in the third quadrant because it is a generation. And the first quadrant, it is the consumption, it is the load. Anyway, that I will come to later on if time permits, as well as your mood permits. This is absolutely semiconductor physics and quantum mechanics. So this energy level we have connected it. So these are the number of, it does not mean that there are no holes here. Only few holes will be here in the valence band, but more number of electrons are there. Here few electrons will be there, few electrons, more number of holes are there. So the point is that, and you find in the structure there is an asymmetry. In a normal PN junction diode is asymmetrical. There is another difference, but you see this is bending. So bending means this is a band, and this band has become bending. So this is a band bending gap. So until and unless we create an asymmetry or band bending in the PN junction, whether it is silicon or germanium or cadmium sulfide or gallium or whatever may be the compound or the element, until and unless we bring the asymmetry in the material, we cannot generate electricity. And you see, this diagram is highly asymmetrical in nature. This is the idea. So first point, we have given some asymmetry to the structure. for generation purpose, what is not there in the normal PN junction triode. Try to understand the difference, because we have to make this Fermi energy level at the equilibrium state. Very, very important. And these electrons, now what will happen in a natural process, if there are say 1000 electrons are there and 2 electrons are there, naturally the 2 electrons will try to come. It's a natural process. If 10 electrical engineers are there and 1 electrical engineer is there with the 10 chemical engineers, so that 1 electrical engineer will try to come with the 10 electrical engineer, because their discussions will be similar type. Similarly, 2 or 3 positive holes which is there in the valence band in the N type, they will try to go. That's the natural tendency of the system. They will move up. So these electrons will never go up to the hill. Rather, these few electrons will down to the hill, and these positive holes will go up to the hill. These holes will never come down to the hill. So the whole concentration of this side will be more. What we have claimed as a p-type, and here the negative concentration, what we called as the free electrons concentration, will be more. So in any device, if there is a positive hole concentration in one side and negative hole concentration in one side, as per our Ohm's law, there is a potential gap. There is a voltage difference, because this side consists of fully free electrons and this side is fully free holes. So again, let me tell you in this webinar what are the research zone from the energy department, where the photon particles will fall. Because nowadays material science is very important component of electrical engineering. It's not that the important component of the metallurgical department, because the electrical engineering department is related to energy is related with the material science, because whenever the photon particles will come with this depletion layer only. So we have to widen this depletion layer. So that is another challenge to the engineers, how to widen this layer, how to give more concentrations of this. Whenever this delivery, you will find in every sentence there is a research zone, and in fact the research is going on. So in every aspect you can publish the paper. Such a wide domain it is. This semiconductor physics, this electrical energy, conversion, efficiency, and all that and all that. Here we will come this part again later on, but from every idea you can have a question to me and I can tell you that is the research zone, you can do it to increase the efficiency of the solar cell. Anyway, so these are the electrons concentration in this side and the proton concentration. I mean the whole semiconductor, instead of proton we say is the positive holes or concentration. So naturally there is a voltage gap. But this voltage gap does not matter much. If there is a voltage gap, how does it matter until unless you use Ohm's law? So we have to put some metal substrate here. This is the metal substrate by the different color. So the metal substrate, the electrons will be accumulated, and in this metal substrate, say aluminium or copper, these positive holes will be concentrated. So we can claim it as an anode, and you can claim it as a cathode, because electron concentration is here. And if we connect this thing through some external agency, current is flowing. So photon came from the radiating energy from the visible part, fall into the depletion part of the, say I have given one example, one atom only. This is not that one atom, you know the Avogadro's number, within 1 centimeter square material, 10 to the power 23, or those who are from the chemistry background or very good knowledge, they can say 10 to the 23 atoms are there in 1 centimeter square material. So imagine, if I'm correct in the Avogadro's number, but I am discussing only for one atom for the simplicity sake to make this thing understandable. So if you connect the voltage difference by an external circuit, and as per the classical definition or traditional definition of current always flows from the higher potential to the lower. So anode if you consider as a positive, and negative if you consider as a negative, so current is flowing to this side. And from this side, as because it is a positive, holes are always positive, as because it is electron negatively charged, so this is positive and this is negative, and the current flowing, so it is a DC current. So photovoltaic source is a DC source. And one point let me clarify here, this is a current source, not a voltage source. From the name itself, it is little misleading. Sometimes I put this question to my students in Grand Viva, photovoltaic source is a voltage source or a current source. From the name they tell it is a photovoltaic, so voltage name is there, what is there? So it is a voltage source, but absolutely wrong, because the electrons are going to this side, holes are moving into this side. So the electron protons movement forms current, not the voltage. So it is a current source. I'm not going to explain what is current source and voltage source. You have studied in your first semester electrical engineering. Just for simplicity sake, I can explain. In our domestic purposes, I am charging my laptop with my source, the socket, wherefrom I am extracting the electrical energy. That socket is a voltage source. Voltage is not a current source. Because in my domestic level, the voltage is 220. If I connect laptop as per the load, current will flow. If I connect 100 watt, so the current will flow according to my load. That load cannot change the voltage level. Voltage 220 will be available in my socket. So that is a voltage source. Photovoltaic cell, remember, is a current source. Current source. Remember it. Even though that terminology is photovoltaic, don't get confused. It is a current source because movement of protons, holes, and electrons are forming this current. So some external resistance are connected and current is flowing. So I have explained how the photons are getting converted to flows of electrons and holes, and we are getting current. Now let us, as because all electrical engineer students are attending this webinar, so let us go to some electrical engineering aspect. And I don't want to concentrate much more in semiconductor physics or quantum, you'll feel bored. So let us go to. So I have given in a single diagram, this is the substrate metal, this is the metal substrate, this is P layer. P layer generally thicker than the N layer. The reason is here, I cannot explain all the reasons because the light will come from this side, it will fall on the N layer. So N layer should be thinner compared to the P layer because light is to be absorbed up to the junction. Then only it will create positive holes and electron, then only able to get the flow of proton, positive holes, and then current will come. So this layer will be relatively thinner compared to this one. These are the design and the manufacturing process of the cell, and this is the total solar cell. The top layer is this is the glass lens top layer. Solar radiation is coming in the form of photo light from this, and this is the N layer. The yellow part is basically the depletion zone. The lower one slightly green based, this one is a P type, and the black one is the metal substrate. And you see, this is a white or the metal. Because until and unless you put the metal in a very, that again let me tell you, putting metal is again an optimal question. If you cover the total surface of the N layer by a metal, how the light will be absorbed into this? So you have to put the metal on the top of the N layer in such a way that is again a research domain, how to put the metal substrate on the top of the N layer so that it can optimally design this cell. I have shown by two parallel metal plates, but there is again an optimal distribution of the metal plates on the top of the layer so that it will collect the electron charge, negative charge, and finally these two things are connected with the see, the negative part is connected with the red part with the positive. Okay, and the symbolic representation of the ordinary PN junction diode, the diode you have used in electronic circuit, there is no these two arrow. Two arrow means photon is coming and falling. So this PV shell implying it is a generator. It is not consuming. When these two arrows will not be there, there is an ordinary PN junction diode. It consumes power rather than the generation. So what is happening? I have already explained, but let me explain a little deeper. Whenever the photon energy, because I am going to the efficiency part of the solar cell, even though in 1954 the solar cell is invented by Bell's laboratory in USA, but that solar cell is not for this ordinary power generation purpose. This solar cell they invented for the satellite and space technology. But again the question is, because the space people can afford it, NASA people can afford the money for greater efficiency of the solar cell. But my institution, IIEST, cannot afford $10 trillion for improving the efficiency of the solar cell because our hand is tied up with the government, this much money will get it. So finally you have to come down the technology, the economic aspect, and the efficiency and the loss system, and that you want to explain. Whatever the solar cells they use in the space technology, because whenever the satellite go to the top, we cannot supply this electrical energy what is available from Calcutta Electric Supply Corporation or division. We cannot connect a wire to the satellite that will give on. So they have to generate energy in their own. So until and unless they develop the photovoltaic cell, they could not send the satellite in the sky, because they need some energy, and that energy will come from the radiant energy converted. But they are having a huge amount of money for that. They invested, and the higher efficient solar cell they invented for the space. But we are all human beings, for mankind, for our simple utilizations for this electrical energy, we cannot afford that much amount of money. So we need normal solar cell where we will sacrifice a little bit of efficiency, but it will serve the purpose. It will not affect our climate. It will not affect our health. Never corona kind of thing will come, repeat in our planet again. So that kind of thing we have to think, and that kind of solar cell we have to produce. Again, research. So what are the photons are coming? I have calculated for red photon 1.773. But you have to choose the material in such a way, you know what is the energy gap? Energy gap is nothing but the energy between the valence band and the conduction band. And we know no electron can be there within this thing. If I can go back to the previous slide, let me tell you, no electrons can lie here. Either the electrons will be there in the conduction band or the valence band. The way, if anyone goes to Bangladesh, this side is India, the side is Bangladesh, and there is a two border. That border is known as no man's land. In no man's land, if I go and where I want to live, no one can live there. So this area, no electron can stand here, can live here. Either the electron live in the valence band or the conduction band. So this is the energy gap. And that's why it is called forbidden energy gap. Forbidden means this is, we cannot allow anybody, the way no man's land, nobody is allowed to live there. Either you have to live in India or you have to live in Bangladesh side. In no man's land over. So no electron can live. So this is known as forbidden gap. So now we have to calculate the forbidden energy level. So let me go again to that slide. So we are trying to calculate the forbidden energy gap. What is forbidden energy? Forbidden energy, it varies from metal to metal. For silicon, it is 1.1207. For germanium, say it is slightly lesser than that. So for material, so we have to choose the electromagnetic spectrum from the vision part of view. This is another research domain. We have to choose a material in such a way that forbidden energy level will be matched to that. Say, if I choose a material where the forbidden energy gap level will be 1.773, then all the photons will be utilized for converting electrical energy. If the photon's energy less than the energy gap, that energy will go in vain. That energy will be wasted, because in quantum mechanics there is another important chapter that I'm not going to cover. The thermodynamics law plays an important role. I'm not going to cover the it's a huge topic, let me tell you. The thermodynamics, so with the help of the thermodynamics law, if the photon's energy is lesser than this energy, that photon cannot knock out the electron from the valence band, usually. Go ahead and again, if the photon energy, say it is required 1.127, and if a red light photon falls onto that, that is 1.173. So what will happen? This electron, I am showing in another diagram. No, it is, this diagram is not there. So let me come back to the previous diagram again. If a photon from the red light falls on this side, so the electron will knock out from the valence band and it will go above the conduction band. But we need the electron in the conduction band. We need photoelectricity. So what happens? Again, we have to bring back this electron which is going beyond the conduction band to the conduction band. So again, certain amount of energy will be wasted in the form of heat using thermodynamic laws. Somehow the electrons should be there in the conduction band within the material. It is not that the electron is going out from the silicon or germanium or cadmium sulfide. It is very, very important. So that is another issue. You have to choose a material. So material science is developing like anything in such a way. Say, let me tell you, we are not lagging behind. Just for example's sake, as far as the solar energy is concerned, we are in the, if I'm not wrong, maybe my students are there in that, we are in the 5th or 6th position in this planet, in this world. First is Australia. Almost, you won't believe. Whatever the coal we are getting from Australia, mostly from Thailand, the good quality coal from Australia. But they don't use coal. They are doing their business. They are giving this coal to this developed, not would be developed or underdeveloped country and going with the good business. They are utilizing their sun. Almost the total energy they take from sun's energy. Solar energy, absolutely full Australia, whole Australia, which is not a country, it's a continent, completely dependent on solar energy. Denmark, completely dependent on wind energy. Even in the evening time, they sell the wind, not sell. If consumers takes the energy from them, they will pay the price. When we consume the energy, we pay the price to the people who is giving energy. But in Denmark, in the evening time, if I take the energy, they will pay power. They will pay money because their energy is surplus mode, and that energy they cannot throw because the energy coming from the wind. They cannot ask on stop blowing now. You cannot blow now because energy has become surplus. So that energy they have to give to the consumer in a free mode. But see, so the science is moving like anything. So this is the quantum mechanics, and this part is going, and we have to bring the photon energy within this range, and the material have to choose, the which part you have to choose. So these are the lot of issues are there that we have to think. And so asymmetric structure, construct the solar cell, outer circuit will be connected and all this. So the question is the efficiency. We know the electrical energy efficiency is very, very good. Very, very good. Say if the DVC produces power and sends power to the Calcutta side or the Connaught Place of New Delhi, the efficiency of transmission the tune of 95%. So electrical energy is a very good quality. Wastage is very less compared to other forms. Compared to mechanical energy, heat energy. Say if I want to talk from here without this internet and all that, it will go only for a few feet. After that, it will be lost. With the help of a conveyor belt, I cannot bring coal to Connaught Place of New Delhi. We can bring coal only few miles or few kilometers. That's all about the mechanical energy transmission. But as far as the electrical energy is concerned, doesn't matter much from one part of the planet to another part of the planet, we can transmit the energy with good efficiency. But the moment when we talk about the solar efficiency, it comes only in the 15-16%. So let us look deeply why it is happening. So efficiency is very simple. I have started with a very simple definition. This is in fact my class note. So P out by P, possibly you have studied in your class 9 standard physics. Output by input is nothing but this. So output is nothing but Jm, Vm. Jm means the maximum power. So there, let me explain you here. You see, whenever you talk about the characterizations of any device in electronics and electrical, we go for VI characteristics. So in case of a normal sink type of diode, the VI characteristics possibly you know. This is the VI characteristics. This is the VI characteristics in the first quadrant because that is a sink. But in case of a photovoltaic diode, it is not a current because we are getting current in a certain amount of area. So better to represent by J. But sometimes the author takes the letter I instead of J for simplicity's sake. In fact, in my explanation, sometimes I have considered I. But correctly speaking, it is not current, rather the current density because you are extracting current from a certain amount of area of the photovoltaic cell. Sure. So this J will come in the third quadrant. And if this is VM, this is JSC. JSC means the short circuit current density, and this is V is nothing but the open circuit voltage. And we plot a curve, we plot a characteristics. Every point is the operating point of that solar point, and at a particular point we will get the maximum value. Because in the operating point, in every point we will not get, because we know that DC power is nothing but V into I. If you multiply V into I, at every point you will not get the maximum power. So we will get the maximum power at a particular point. So this is nothing but Jm into Vm divided by, if you take a parallel line to the V axis, VOC, and if you take a parallel line with VOC, JIC, I mean when IC is maximum, VOC is 0. When VOC is maximum, then JSC is 0. If you take a rectangular, then you'll be able to calculate the power. So this power divided by this power, IM VM divided by JSS into VSC is nothing but the fill factor. So fill factor is very important term, a very important term in a solar cell. This is the fill factor. Fill factor, because sometimes I have found or heard from my students, sir, you told I have purchased on solar panel, not solar cell. Solar cell is the smallest unit of the solar panel. I have purchased from the Chandni Chowk, but it is not working because they have not mentioned the field factor. They have to explain the characteristics of the cell. Sir, I have paid 1,000 rupees, but see, they have written 30 volt solar panel and all that I have brought, even though the panel is 30 volt, but see, a small LED is not working with that also. But I have paid 1,000 rupees with the Chandni Chowk. Maybe it is Chinese make and all that. But the question is, these characteristics is very important, not VOC and JC, because within this point I can draw a straight line. I can put this type of curve. So until and unless on the panel there is a characteristic, you should not purchase the solar panel. There is very good student, they do not know up to much. They do not know what is full factor. Just like that CKC has told and purchased, then no, sir, it is not working in our project. How it will work? Because they do not know this much in details about the characteristics of all that. So efficiency in terms of field factor, because I have substituted this value. These are all simple mathematics. In fact, 11, 12 standard mathematics I have substituted. So efficiency can be written in terms of field factor. That I have getting this. So now the question is air mass. I do not know how many students know about air mass and all that. Whenever we calculate the radiant energy in the photosphere, I mean not in our Earth's atmosphere, we call it air mass zero. Air mass zero means no hygroscopic pressure, no humidity, no aerosol, no particle, no dust, no dirt, nothing is there. But the moment this radiant energy will come into this, the air mass is continuously changing. And in fact, the air mass of Durgapur and air mass of Calcutta is different. Because of the atmospheric and because the Durgapur steel plant, huge amount of pollutants are all there. If you air mass you can calculate with the device. If you calculate the air mass of Durgapur, if you calculate the air mass of Hara, if you calculate the air mass of Silchar, where huge forestation is there, it will be entirely different. But this AM0 or AMO is the air mass 0 beyond the atmosphere. And let us consider AM1, this air mass 1. And air mass has got a definition. Air mass means this radiant energy is coming through a path. Coming through a path. So coming through a path. So when sun is on the top of our head, the distance covering the path, and whenever the radiant energy coming through a curvy path, the ratio is nothing but the air mass. That's another. And from that air mass, what we can do? We can calculate the number of photons. Because in every centimeter square silicon, maybe there are 10 into 2. Please rectify it or see later on from the Google Chrome or the internet resources. 10 to the power 23 atoms are there. I'm talking only about one atom. So how many photons are coming? We have to calculate, and that photon is to be matched with the number of atoms. I have invited 10 people, so I have to prepare the 4 for 10. If I prepare more than 10 people, it will be wasted. If I prepare for 7, then there will be deficit of 3. So I have to choose the material in such a way. You have to choose the air mass in such a way. You have to. But the question is again, how much radiant energy will come from the sun? We cannot control. Only God can control it. Nobody in this planet can control it. The president of America, president of India, no man in this planet can control the radiant energy. Yes, this much energy has to come. No one can dictate sun. Only whatever we can do, we can free the environment little bit from the pollution. So that we can improve the air mass. Otherwise, no other way out. So we have to calculate the number of photons to improve the efficiency. So photons, so number of photons per centimeter square, per centimeter square, per second in 20 nanometer wavelength. I have chosen the wavelength just 20 nanometer length of the red light. And if I go for the cycling integration, then we'll be able to calculate the photons. We'll be able to calculate the photons. So the solar energy extractions using of the material, quantum mechanics, quantum tunneling, air mass, everything is this. And another important thing, I have in fact delivered more than one lecture, all in the favor of solar energy, but a lot of disadvantages are there. Sometimes the cloud makeup, sometimes continuously the way is going on, complete raining is going on throughout the day, sun may not be there. So there is another aspect, you have to store the energy in the battery. Once you're able to store the energy, battery is the battery management. So storing is a new research domain, I can tell you. How to store is not that our ordinary battery, lithium and battery in a cell, I'll store it and go for a delivering. So storage is a completely new domain. And last 4 or 5 years or 10 years, we are talking about the storage because of the solar energy. If the energy is available, if you cannot utilize, you have to store it. And once we can store how to manage it, that is a battery management is another research domain. And all the important ACA journals have given their different tracks. For battery, IEEE transaction is a track. Battery management system is another IEEE transaction track. Solar energy is another track with solar cell. In every renowned journal, they are doing all these things. So every point is a research domain nowadays. So anyway, let me come to the original things. So we are calculating the photon share. So check why it is impossible for the human being to bring 45%, 50% efficient of the solar cell. Initially, I assumed 100% solar. So no absorption. Whatever the energy is coming, by that device, energy will not be absorbed because the energy which is coming is lesser than the energy gap, 23% gone. Out of 100%, 23% wastage. We cannot accept that energy. Okay. Then excess photon energy, whatever the energy is coming in the form of a radiant in the vision zone, their energy is more than the energy gap. That is again absolutely wastage in the tune of 29%. But in fact, this data varies from material to material. I have considered for silicon. You see on the top I've written silicon 100 micrometer thickness, but it does not mean this is true for other things. I'm talking only for silicon. Remember, it is not true for cadmium sulfide, it is not true for germanium. For germanium, again, this data will change. Again, VOC means even though short circuit current is 0, total VOC is available, okay, but it does not match with the voltage band. So again, some loss is there. Fill factor loss is there. So a lot of losses is there. So at the collection efficiency, whenever we will connect the PN junction to a metal, some interfacing difficulties will come, and that interfacing will create some resistance. So that resistance will again go in the form of a loss. Again, a lot of electron and hole, even though the photon is creating the electron hole pairs and free electron, after certain amount of time, those electrons will combine in the holes. So that energy is wasted. That is known as the recombination theory. Another idea of the photovoltaic cell, recombination. For the recombination, the RSH has come. So that again an wastage. Should be clubbed together. Recombination and contact and surface loss it will be the tune of 4%. So finally we will find almost, you see, come to be 29%, 23%, then 14%, then 5%, then 4%. Almost it will be coming in the tune of say 70 to 73%. Only 27% is left out. That too for a mediocre grade of silicon. I mean the solar silicon. It is not that the electronic silicon I'm not talking about. So how can I improve the efficiency of the solar cell by the computer technology, information technology, blockchain, all that? Because these are all gifted by God. So another aspect, you have to choose the material, they choose in such a fashion, we'll be able to improve. The way the space people, the Bell the laboratory can do it, but that is not feasible for this. But anyway, for academic interest, for theoretical interest, at least in our laboratory, we are able to develop 30 to 32% efficiency in our laboratory, and we are supplying Vikram Solar. So this is all about. Now, once we get RSH, collection efficiency loss, and all that, we can able to develop the equivalent diagram. This, I already told you, this is nothing but a current source. So current source I have represented I photon. And remember, this is a variable source. Because the solar irradiance, again I told you, we cannot change it. We cannot change it. The solar, we cannot control it. The way we can control coal. So this time there is no industry opening, students are not coming to the institution, light, fans, ACs are off. So electrical consumption is less. IIEST has to pay less money to the CSC and all that. So CSC can control their generation by controlling the input, means coal. But this, as far as the solar energy is concerned, no, today student is not coming, please do not give this much amount of radiation. So we cannot control this solar input. So this input is a current source, but continuously varying in nature. Another important aspect is the dark current. Even though there is no solar rays or radiated rays or the thing, still in the evening time, there is a diffused light. Diffused light. Because of the diffused light, solar cell can generate a small amount of current through the cell only. If you connect through the external wire, you won't get any current. But through the cell, certain amount of that is known as the dark current. And there is a new area. And from the dark current concept, again, 17 scientists got the Nobel Prizes from the dark current of the diode. Imagine what a field. 17 scientists got Nobel laureates from this dark current of the photovoltaic diode cell. Let me tell you from the statistical point of view, what we do. And there the research is going on how we can utilize the solar cells in the night also. Solar cell, even though the thing is coming from the sun, how to utilize the diffuse light such that at midnight the solar cell will able to develop the power and there is no question of storing and all that. So the thing is going on in a really different. In fact, few days back I got another information. I will update you and then I will close this lecture. So this is the dark current. Dark current means this is the current which is flowing through the cell in opposite direction. So this is the negative side. It will go from the main current. The main current is going to the resistive. This RSH is again a current what we are not getting from the outer part of the circuit, that the recombination. Few electrons after generation will be combined to the holes, USH. And RS, I have already explained, it is come in the junction type. When the silicon will be clapped with the interface with the metal, some kind of resistance will be there. This is RS. So this is the equivalent diagram of this. And this is the dark current expression. This is not the dark current. This is the ID, diode current expression. I0 is the dark current into e to the power QVD divided by gamma KT minus 1. Gamma is nothing but the curve fitting from the metal. For silicon, it is from 1 to 3. You can choose one. K Boltzmann's constant. T is the temperature at Kelvin, absolute temperature. Vd is the voltage across the diode. Q is charge of an electron. So this expression is very popular expression. And this QVD by gamma KT minus 1 dark current, again one Nobel Prize. So see, just what an expression, what Nobel Prize. So that I think and sometimes what lot of things we develop. But what they have developed in the quantum level have brought the Nobel Prize for them and they have the Nobel laureates for them. So if we go back, because I cannot show the slide side by side. So if you look at this thing and for the simplicity's sake, now I have to move fast. If it's for simplicity's sake, say all the electrons are delivering current, there is no recombination, RSH is not there. Say I photon minus ID will be IL. I photon minus, I have substituted the value of I0 is equal to IL. So I have changed the side from the right side to left side. I have brought the terminology and I have taken both sides the natural logarithm with a base E. Then my target is you have to plot the characteristics. Whatever the cell will develop, you have to check the characteristics. Until and unless we know the characteristics, you will have to purchase the material from the, because the fill factor does not give you a clear indication of the cell. So we have to take these characteristics, and for that reason, we have to calculate VL and IL separately. So that is our target by the mathematics. Then this is very, very simple. This IL, I have brought this thing, then I have taken these things, and then when RL will be 0, when load current IL is 0, let me explain you. When IL is 0, here it is 0, here it is 0, then you see VOC. When IL is 0 means load is open, then you will get the open circuit voltage. VOC will be gamma KT by Q, ln I photon by I0 plus K. And all the things are available. Charge of electron, you know, gamma, the curve fitting value, you 1, 2, 3, you can consider one, no issue. K Boltzmann constant, standard value. T is the temperature. At what temperature you doing the test VOC, you just add with 270 and get the result. So it's very easy to calculate these things. And our students in a laboratory, they calculate with the solar cell. In a smallest unit, they calculate VOC. And if we now calculate, if we consider the RSH, I have just added RSH means a certain amount of current will flow here, because main current is now being reduced because of the recombination. So minus ISH is equal to IL by using Kirchhoff's current law. I photon minus ID minus ISH is going back, is going to the IL. Again, I have substituted the value, and this is the expressions. And if we plot this curve, so this is the expressions. So this is load current, this is load voltage. When VOC is 0, this is ISC. When ISC is 0, this is VSC. And if we plot the different operating point, this is the characteristics. And the, you know, the area under the curve is always nothing but the area that we have studied in a definite integration. So this is area. So you have to calculate the area, which area is bigger, which area is larger. So let us say at this consider the area is maximum. So here you'll able to extract the maximum power, not tracking MPP. Is not that so? If I get ISC and VOC and if the curve is a straight line, obviously the MPP is different. And how will you able to calculate your LED with the solar cell? Because they have cheated you, they have taken 1,000 rupees, but they have cheated you. Because the characteristics is important, because in between these 2 points, I can go for 1,000 characteristics. Whether they have drawn the characteristics on the top of the panel is very important, you have to check it. Otherwise, it is absolutely useless. And fill factor definition that have, and this is the VI characteristics. You see, I have also considered I instead of J, but it is J. And if I take the different values of power in the different operating point, this is the power characteristics and this is the maximum. Now here sometimes the student asks, sir, you are talking about one cell only, one unit. If I go for a panel, well, that's right. Because from one cell we are getting in the tune of 0.8, 0.7 volt, 0.8 volt. 0.7 volt and 0.8 volt is absolutely useless voltage. With that, with that voltage, we cannot utilize anything. We need 220 voltage. At least we need 30 voltage for operating or domestic pump. So what we will do? Those cells will connect in series to enhance the voltage level. And to enhance the current level, those connected series cells will connect in parallel. So there is nothing but the panel. So the students ask, sir, if we put the VI characteristics of a particular cell, and if we put the VI characteristics of a particular panel, both are same, almost identical. Fortunately, God is kind enough, almost the characteristics, it's a slight difference, but identical. So whatever you can talk about a one shell, for the whole panel, the characteristics remain same. So let me go to the name. So these are all definitions I have covered. Whatever I teach in that class, let me explain. So this is one curve. But imagine this photon current is changing. This photon current, if I reduce it up. So in the morning time, the photon current has become half, and the noon time, this is the photon current. If the photon currents become suddenly, because this current is, because the radiation is continuously changing, so photon is changing. So the question comes from the student side, the voltage will change proportionally? Answer is no. Possibly, we have got the idea, this VL, this VOC, and this current I photon is connected by logarithm. We have studied the logarithm in class 9 standard, but we have not understood the beauty of the logarithm. Doesn't mean it means VOC and IPH is not directly related. If IPH changes tremendously, but VOC will remain almost fixed, and that's the beauty of the logarithm. And you see, during derivation, log h comes. And we can understand logarithm from physical point of view in photovoltaic cell. In normal mathematics, we simply calculate some, we do some solve, we solve some problem, tally the answer at the answer part, and we are happy go to the next sum. This is the beauty of this logarithm we'll able to understand in the photovoltaic cell. But let me explain you, those who love mathematics. And here you see the I photon current is reduced half, but voltage is not reduced to half. And if we consider the maximum power point of the different curves, so from this point to this point, this is another VI curve. If again the current comes down during the evening time, so this is the curve. And if you take a maximum power point trajectory or locus within this bandwidth, this is a band means within this line, this is band means there is a kind of a range. So within this range, the maximum power point will be there. And finally, when I will become 0, this curve will definitely meet at this 0. When I will be there, the photon current is 0, obviously it cannot give supply to the load. So this curve will drastically go to 0. Slowly it will come down and finally it will meet to 0. Sometimes the student asks, sir, if you extend the curve, it will come, it will obviously 0. If the photon current is 0, so there is no current in the load side, so so it will automatically come to this point. So this is very, very, and with the help of simple ammeter and voltmeter, you can measure all these things. It is not required in ordinary way. Even in the power system lab of any engineering college, one solar cell, one solar panel, one ordinary ammeter or ordinary digital ammeter, voltmeter, you can develop labs and we can plot these characteristics, you can maximum. And with the help of the power electronics device, if you can track this thing, then it is called as MPPT, maximum power point tracking. But we are not going to tracking because our idea is to convert photon to electricity. My part is over almost, and what should be the best load for this? Again, the disadvantage is solar cell. If it is a coal-based generation, any load we can connect. I can connect AC, I can connect fridge, I can connect microwave, I can connect any load, I can connect it. But in case of a photovoltaic generation, it is DC, we can connect DC kind of load. That is the most preferable. But if we go for AC kind of load, we have to put in between inverter. But again, inverter is a questionable loss. Inverter is some middleman is coming. It will consume certain amount of power. It will pollute the power. Harmonics will be created. But anyway, whatever it may be, this is the thing this is all about this DC generation and the best fitting load is the DC load. And because it is not a off mode class, otherwise I could have put this question: what is the best load for this photovoltaic cell? The answer is battery cell. That's the best load, charging battery, and that's why another topic has nowadays come: electrical vehicle. Electrical vehicle. So charging electrical vehicle. For electrical vehicle, they require battery, and for battery charging, photovoltaic cell is one of the best. The reason is simple. Even though this current is changing, voltage is almost remaining fixed. And what is the characteristics of the voltage? Characteristics of the battery? Whatever the current we drop from the battery, voltage remains stable. The lithium-ion battery is showing 30% charge is here, 40%, but we can able to work with that 30% because the voltage remains same. So any battery is a constant voltage source. And because of this changing pattern of the irradiance or insulation, voltage is almost remaining fixed. The best load for the photovoltaic cell is battery charging. Again, a group of scientists have taken, even is the best. So make a battery in such a fashion we can utilize in the electrical vehicle and forget this 4-stroke engines and all that, because it is creating pollution. And hopefully you will know the price of fuel has already crossed century, even in the diesel price. And as because the thing is finite, as long as it will be depleting in nature, naturally if the amount is less, price will go off. Even though I do not go the CGS, KSD, political things and all that, if I do not go into detail in my simple layman's language, if the thing becomes less and demand is more, obviously from simple economics theory, price. And imagine 2021, the price of petrol in the month of. So we have to go for such an alternative energy. Price will be absolutely free. No one is going to take charge to take the power from the sun, and absolutely clean energy, not green and pollution free. And this so is the best battery. But sometimes we go for domestic use for the solar pumps. Solar pump, the loads are there. These are the panels. Let me sum up because I am shouting for almost 1.5 hour. I have to stop here. So this is monocrystalline, multicrystalline, polycrystalline, amorphous. Because the efficiency monocrystalline is very good because it is a crystalline structure and very hard. Polycrystalline, the lattice structure is little bit bad, such that the recombination factor will be more. Less amount of current will get from that the photon energy, but we are sacrificing a little bit of efficiency, but the thing is cheaper. And in case of amorphous, we can go for a thin layer photovoltaic cell and we can utilize, but the efficiency is very, very less, in the tune of 4 to 5%. These are all statistical data and the material science is improving a lot. These are the array panel description. This is array, this is module and cell. Solar cell characteristics, merit, demerit, the panel. This is the parallel combination, final characteristics, the single series. And what I told you in the beginning, if you plot the characteristics of a single unit, single cell, and the characteristics of the panel, whether it's a series connected parallel, the characteristic does not change much. So I have come to the almost end. A renewable energy has become a formidable leader of future economy. A shift of focus from bulk centralized generation to distributed generation, near load, more use of sustainable renewable, and it is sustainable also. This energy is going to be finished in 10 to the power 9 years only. So it's okay. Of generation, environmental consideration, health is particularly, automation, application of ICT, introduction of smart grid, microgrid and all that. So harvesting sunshine, conclusion is harvesting money. So let me finish with a very good idea from Thomas Alva Edison. Solar energy is a great idea, possibly no. Thomas Alva Edison is the inventor of incandescent lamp. He is the first man who has laid the transmission line from New Jersey to New York, maybe 100 kilometers length. You can rectify the 115 kilometers length, but nobody knows he was a very good businessman also. Thomas Alva Edison is a very good businessman also. And I should not tell all these things here, but I was fortunate enough in 2006 when I was in USA, I visited his statue in New Jersey, where from he started this transmission line, Thomas Alva Edison. What he quoted, what he told. He told, as a businessman, not as an engineer, not as a scientist, I would put my money on the sun. So imagine 139 years back how he realized about the sun and solar energy. What a source of power. I hope we do not have to wait till oil and coal run out before we tackle that. Thomas Edison told 1882 and 2021, I am taking webinar on solar energy. Anyway, so this is the thing we have to do it. And let me finish, and I've come to the thank you slide. I am putting two questions to my students, the bright budding engineers and the young faculty. During my discussion, I pointed out a lot of research domain. The moment you will pick one domain, you can go on exploring your idea there. Material science, the band, the quantum tunneling, quantum physics, energy conversion, efficiency level, whatnot and whatnot. But this is when energy is coming right from the sun. We are not doing anything. Straight the sun is giving energy. Then why we are digging the earth? We extract oil and coal, we have to dig the earth. We are polluting there. We are digging the earth instead of the energy. What is the question to the students? And another, solar power is the last energy source that is not owned yet. Nobody can claim sun is mine, and nobody taxes the sun yet. Till today, nobody has put the tax, CGST, SGST and all that on the solar power. Then my question once to the student, we have to take, or we have to give proper focus and proper attention to the sun so that you can extract more energy. And let me finish with this. A lot of things are there for updating, but I'm not going to this. Nowadays, the faculty of these things, MHRD, I do not know about the private institution, MHRD has made it compulsory. All the national institution has to generate their own generation consumption in the tune of 30 to 40%, either from wind or sun or from combination or from biomass or biogas, whatever it may be. Otherwise, they will not give you the money. You cannot take this. So there is a restriction for all NITs. And a lot of NITs have developed and they extract the sun's power in such a way. In Kerala, one institution is there, and that is in fact a private institution, 100% energy from sun. They never, and they paid back the total amount to MNRE within 4 or 5 years. The whole institution are moving with solar energy. And in our institution, IIEST, IITs and NITs, there is a compulsion. We have to generate 30 to 40%. I mean, 100 megawatt we have to generate. I did a mistake. 500 kilowatt, not generate. 500 kilowatt we have to generate within this span only. Otherwise, our NIF ranking will be affected. Our money what we receive from them in their budget will be affected. It's a clear-cut information. You have to generate it. Otherwise, you will be in the tightened condition. Your NIF ranking now linked with the from where you are taking this power. So there are a lot of boundary conditions and restrictions are constant from such that if we do not like to generate solar energy, some rules will be there which will bound us to create, otherwise you will be in the trouble. And thank you so much for your patient hearing. So anyway, this is all about from my end. It's a huge topic. I can take more than 5 hours lecture, but as an old man of 60 onwards, I cannot shout for 5 hours continuously. So this is all about from my end. Hand over to the organizer, yes, Professor Sneasi Senal. So you can ask your participants, listeners, if they want to ask any questions to me. But it is, I understand it is a little bit semiconductor related and all that. So I do not know whether any question is there, but anyway, this is let me come back to the yes. Stop sharing. So I am.
Okay. Thank you, sir.
Sharing and okay. Thank you too also.
Sir, can I ask one question, sir?
Oh, surely. Let me come. I want to see your face also. Yeah. Oh, have I?
Yes, sir.
Just a minute. Just a minute. Just a minute. I have to go to my that original this one. No. Okay. Ask me the questions.
Yeah, sir, you told sir that PV cell was working on third quadrant. Is it third quadrant or fourth quadrant, sir?
Oh, I did a mistake. Just below that, fourth quadrant, not third quadrant. First quadrant
Yes, sir.
for PV shell in the sink. I have shown
Yes.
the fourth quadrant by I told that's a mistake. That's right. That's a very good point you have pointed out. That is the third quadrant what I have shown in the pictorial form. That's right. So any questions from the quantum tunneling, quantum mechanics, radiated energy? Any question, because this is absolutely new idea. So you can put any questions to me.
So thank you, sir. Thanks for enlightening us with such a beautiful speech.
No, sir.
This is very informative.
Sir. Well, I have another question, sir.
Okay.
I have another. Yes,
Welcome,
I have another
welcome.
question.
Yeah.
From student.
I can assure you. Welcome. Just
okay, sir. From students' point of view, sir.
yes.
Actually, general simple diode acts on first quadrant, that is a sink, and this photovoltaic diode that is a generator. It is working on fourth quadrant. So,
right.
so can you, if you please explain that transition? That transition.
Let me explain you. That's right. Absolutely.
Yes, sir.
Absolutely. I have already come out from that sharing part, so I am explaining my mouth. Whatever I think. When we consider as a sink, and we plot the current, that we plot current in the positive direction of the y-axis, I mean in the dependent axis, and voltage in the independent axis, I mean x-axis. So whenever we plot, that's an assumption. From a simple mathematics, let me explain you, then you'll be able to clear. So our normal trigonometric angle, we understand whenever the angle moves in the clockwise direction, we always consider in trigonometry that's a negative angle. Whenever we rotate the angle in counterclockwise sense, we consider sine theta. If sine theta is positive, means the theta is rotating in counterclockwise sense. When we write sine minus theta, so that theta is rotating in clockwise sense. So whenever because in somewhere we have to take some reference. Whenever we plot the VI characteristics as a sink, so that current is the load current, and we have taken y-axis is the dependent axis, which is the positive side. Now, as a generator, whenever we plot the current or the current density, whatever, this is a generator current, so the direction of the current will be just opposite of that. If I consider that is positive, so this will be negative, and that's why better to plot the current density in a photovoltaic cell in the third quadrant. But again, I am telling you, if we plot the current density or the current of the photovoltaic characteristics in the first quadrant, then PV shell sink characteristics will come in the third quadrant, because it is a question of a frame of reference. Because normally PN junction diode comes first, then photovoltaic. So that's once that has come in the first, we have taken that one as a reference, and with that reference, and whenever again I tell you in the photovoltaic shell, whenever within the diode, whenever the current flows, that current flows, I told you there is a dark current, where from 17 men scientists got the had achieved their Nobel Prizes. That current, if you plot, that current will come in the first quadrant in the photovoltaic shell. So that current we cannot utilize. That is going as a heat. So that is again a kind of a load current. So photovoltaic current, whenever we consider only the diode current, or the diode current will remain in the first quadrant, but whenever we'll connect that collector, the negative and the positive collector, through the outer circuit with the help of a load, it has become a generator. Now it is supplying instead of consuming, and it will come to the third quadrant from the reference point of view. The way I put a line number, because the origin is 0, if I go in the right side, it is plus. So if I go in the left side, I have to put -5. That's all. The question of reference. This is the thing. But if I plot the characteristics in the first quadrant for photovoltaic, so for PN junction, you have to bring to the third quadrant. That's all. The question of reference only. And that plot depends on you only. because you are having the solar cell, you are taking the voltage, you are taking the current with the digital ammeter and plot it. That's all. And then invert the quadrant. Quadrant is again a concept. That is the thing. So this is all about the point of frame of reference.
Okay, thank you, sir.
Yes.
Okay, Synthesis,
But in a lot of textbook, you will find they are plotting the first quadrant to make the thing simpler. Because in my diagram also, intentionally instead of J, I took I, and instead of the third quadrant, because third quadrant, we have to look in the third quadrant, in the opposite direction, that looks a bit clumsy and difficulty. So everything off, and I brought in the first quadrant and I did it. But the philosophy, the physics behind the photovoltaic semiconductor will remain same. No change at all. No change at all.
Okay, thank you, sir, for such a valuable speech. So we are almost come to the end of this session. So before going to
Any questions from your chat box? Any questions?
Yes, before going to the concluding remarks, I just want any question from the students or the audience.
It is related with the semiconductor physics and quantum mechanics. Intentionally, I have avoided the mathematical part. Otherwise, it will be a little boring also, because in quantum mechanics, there is a huge mathematics are there. Intentionally, in my presentation, I have avoided it, because I wanted to explain everything in the explanation form. It's very interesting, and research. Why I explained this I told, they really did entirely new domain of research. We are now talking about the renewable energy, we are talking about the environmental security, energy security, economic security, all we are talking about security, but all the security will come from these renewable energies. That is the ultimate thing. Without energy, cannot do anything. That's why I picked up this topic.
So, if anybody have any question, you can please ask.
So anyway, thanks a lot for hearing. It's a little tough also, let me tell you, because it's related with the semiconductor physics and all that, because in electrical engineering, directly go for the application part. But here I talked how photon will be converted to electricity, completely in the nano level, the thing is working, and the material level and the conversion is absolutely semiconductor physics and the quantum mechanics is working. Maybe students may not be interested or they cannot go up to that level. So that's why they are not putting, but once they grow their interest in this domain, I think it's okay. It's okay.
Okay. Okay. So, with the permission of HOD sir, SB sir and director sir, they are here already. So, with your permission, should I put the concluding remarks to this session?
Yes.
Okay.
No, carry on. Yeah.
Okay. So, thank you all for attending today's webinar. I want to convey my sincere thanks to CKC sir for sparing his valuable time with us. Being a scholar of him, I really know that how much busy schedule he has as an administrator in IIEST, even in this pandemic situation. I really don't know how he manages time so judiciously and put equal efforts in all of his activities. I request sir to spare some other time to teach us on something on this. Now, on behalf of the...
I'll do that.
Okay. Yes, sir. So, on behalf of the BCREC fraternity, we are really fortunate enough to get such a wonderful session with you, sir. I would like to thank our director, sir, other dignitaries of BCREC for their valuable presence. I would like to thank Dr. Shushanto Datto, HOD Electrical, for his constant support for this webinar. I want to thank Professor Shumit Banerjee, sir, for arranging this exciting and informative event on a socio-scientific issue amid such a depressing situation. I want to thank all of my colleagues, particularly Kinshuk Mujumdar, for their constant support to this webinar, and of course, our beloved students, without whom this event would not have been successful. Thank you all. Thanks a lot. With this, we are declaring the ending of today's session. Stay safe and protect yourselves. Thank you.
Okay, thank you, all of you, and thank you, Director Sher. Okay.
Supplement one comment. Before you,
Yes, sir. Yes, sir.
I just want to supplement one comment. I had some work during this deliberation. Believe it or not, the way the they use oxygen. I really thrilled. I hope that our professors learn how a complicated things can be spoken, can be delivered in a lucid manner. This is the question. Professor, thank you very much. And
No, thank
correct.
you, director, sir. Thank you, director, sir. Maybe I'm not that much. Okay.
Leader, actually, renewable energy has become a formidable leader.
Yes,
of
absolutely.
That is very true. Because
Very
now,
true, very true.
what is happening in our country, that is 22.8% we are dependent on hydro, 64% on thermal, 3% on nuclear, and 10% only on biomass. So this
Right.
renewable energy is definitely a future, unless and until that we have already told that we are unable to utilize the energy that is given by the sun, then there is no future actually. The way the population is growing, the way the demand is growing, unless and until we invent this renewable energy, our future is going to be. So I think that the professor has given us a new light. Susanto, as well as Sumit, I would request that please bring professor in our college and the communities forward so that he can interact physically with our students. It will be really immense help for us. That much I can say. Thank you, Professor. And
Okay, thank you, sir.
you.
Thank you, director, sir, for your. It's okay.
Thank
Thank
you,
you
sir.
all. Okay, thank you all.
Sir. Thank you,
all.
director, sir. Thank you, everybody.
Thank you, sir.
Okay, thank you.
Okay. Thank you all. So can I leave now?
Yes,
Yes,
sir.
sir.
Yes.
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 Okay. Thank you all for your.
Thank you.
Okay.
ভাই সুমিত, থ্যাংক ইউ ভেরি মাচ। এরকম তো
হ্যাঁ,
একটু কম শুনেছি। দ্য ওয়ে হি স্পোক কন্টিনিউয়াসলি 2 ঘন্টার উপরে বলে গেলেন।
যাক, আমাদের ছেলেদের ভালো লাগলো স্যার, এটাই ভালো স্যার।
দ্য ওয়ে হি স্পোক, এরকম একটা ডিফিকাল্ট সাবজেক্ট এত সুন্দর লুসিড ম্যানারে বলে গেলেন, ইট ইজ রিয়েলি রিমার্কেবল। তুমি এই প্রফেসরকে আনবে এবং আমাদের কিছু ছেলেগুলোকে
নিশ্চয়ই স্যার, নিশ্চয়ই স্যার, নিশ্চয়ই। হ্যাঁ, নর্মাল হলে নিশ্চয়ই নিয়ে আসবো স্যার।
থ্যাংক ইউ ভেরি মাচ।
থ্যাংক ইউ স্যার, থ্যাংক ইউ। ওকে, থ্যাংক ইউ স্যার।
Thank you. Thank you, Director, sir.
Thank you, sir.